Welcome to the dawn of the 6G era, where the boundaries between communication and perception are finally dissolving. This is the future of the hyper-connected world. Vehicle-to-everything communication has evolved from simple data exchange to a complex multimodal sensing network that defines our movement. In the 6G vision, every vehicle is not just a node that talks, but a high-resolution sensor that sees its environment with pinpoint accuracy. To understand this shift, we must distinguish between localization, finding connected devices, and sensing, detecting unconnected objects in our path. The engine of this change is SideLink, or SL, which enables direct communication between devices without the need for a central base station relay. By bypassing the core network, SideLink slashes latency and signaling overhead, which is absolutely crucial for safety-critical 6G applications. Ongoing standardization efforts, starting with Release 18, are now bringing sensing and localization into the heart of the SideLink architecture. Today, Mode 1 allows the network to manage resource allocation, ensuring stability and coordinated communication in dense traffic environments. In contrast, Mode 2 empowers vehicles to manage their own resources, providing critical resilience in areas with poor or no network coverage. Localization in 6G is about more than just coordinates. It's about achieving sub-meter accuracy to support the highest levels of vehicle automation. To achieve this precision, the network utilizes various SideLink measurements to estimate both the relative and absolute positions of every device. Round trip time, or RTT, measures the precise time for a signal to bounce between devices, creating a highly accurate distance radius. Time difference of arrival, or TDOA, uses the arrival time at multiple receivers to triangulate a vehicle's position with mathematical certainty. Angle of arrival, or AOA, determines the specific direction of the transmitter, narrowing the search space down to a single precise vector. Sensing takes perception further by detecting objects that aren't even part of the network, ensuring safety for pedestrians and other road users. In monostatic sensing, a single vehicle acts as both the transmitter and receiver, functioning as a localized radar for its immediate path. Bistatic sensing involves multiple vehicles coordinating to detect reflections, providing a richer, shared 360-degree environmental map for everyone. The 6G architecture relies on various roles, the target UE being localized, reference UEs providing fixed points, and located UEs with known positions. Frequency selection is a game of trade-offs. FR1, the sub-6 GHz band, offers excellent coverage and superior obstacle penetration. However, FR1 is limited by narrow bandwidth, which restricts its ability to distinguish between closely spaced objects in a dense urban environment. FR2, or millimeter wave, provides the massive bandwidth needed for high-resolution sensing and centimeter-level localization accuracy. However, FR2 signals suffer from high path loss and are easily blocked by common obstacles like buildings, rain, or even trees. To overcome this, 6G systems use massive MIMO and advanced beamforming to focus signal energy into narrow, powerful, directed streams. This creates a powerful synergy. Sensing data helps vehicles predict movements and keep these beams perfectly aligned in real time. Integrated Sensing and Communication, or ISAC, is the 6G vision where a single signal serves both purposes at the same time. Urban environments are messy. Multipath interference, signals bouncing off buildings, can create ghost detections and timing errors. Advanced signal processing and deep learning are being deployed to filter out this noise and find the true signal in the chaos. With thousands of connected vehicles, the risk of multi-user interference escalates, demanding ever smarter resource management strategies. As we rely more on these signals, security becomes a primary concern for the safety of autonomous 6G systems. Malicious actors could inject false information or jam signals, potentially causing chaos. 6G must be built with zero-trust security. Countermeasures like signal obfuscation and robust encryption are being built into the very foundation of 6G to protect user privacy. Looking even further, sub-terahertz frequencies, or FR3, promise extreme resolution for mapping the world in near-photographic detail. AI will play a massive role, predicting vehicle movements before they happen to keep high-frequency beams locked and stable. Standardization is the final piece of the puzzle, ensuring that these innovations work seamlessly across borders and manufacturers. This technology enabling smart cities where every infrastructure element helps map the world in real time, aiding every vehicle in its path. The 6G horizon is closer than we think, and the fusion of sensing and communication is what will take us to the next frontier. To recap our journey into the 6G future, we've explored how sidelink evolution is breaking the silos between communication and environmental mapping. From the foundational methods of RTT and AOA to the cutting-edge implementation of ISAC in the sub-terahertz bands, the future is built on synergy. We've addressed the critical challenges of path loss and interference and emphasized the non-negotiable need for security and privacy. As we look toward extremely large arrays and smart city integration, it's clear that the network itself is becoming the world's most powerful sensor. This convergence is the defining technical challenge and opportunity for the next decade of wireless innovation. We are moving from a world that is merely connected to a world that is truly aware. The 6G revolution is here, and it is sensing everything. Thank you for exploring this frontier with us. Stay curious, stay informed, and let's build the future together.